Our last problem here in our thermodynamics chapter, chapter 20, allows us to think again about the temperature dependence that we have for equilibrium constants, and we see that through the temperature dependence here of free energies. And just to remind you, in chapter 17, when we were learning about equilibrium, we saw the Van Hoff equation. And so I'm just going to remind you what the Van Hoff equation was. The Van Hoff equation tells us that the natural log of the ratio between two equilibrium constants is dependent on the delta H of the reaction over R times the two different temperatures that we had. So again, this is the Van Hoff equation. We're not going to do anything with this equation right here, but it just was an equation that reminded us that there is a temperature dependence on equilibrium constants. And we're going to kind of see that played out here as we look at the chemistry for sulfur trioxide formation here. And it's kind of hard to see the equation here. So this is the equation for the chemistry that we're looking at here. 2SO2 plus O2 makes 2SO3 gas. And so there's three parts to this problem here. The first is that they tell us that there are two different delta G naught values, one at 298, and that's equal to minus 141.6 kilojoules per mole. So I'm grabbing data here from this first part here. So the delta G naught at 298 is minus 141.6. And just to remind everybody again, when we see this little naught, that means we are at standard conditions, which in this case, if we're talking about concentrations, it's going to be molar, and if we're talking about partial pressures of gases, it's going to be 1 atmosphere. So that's what that little symbol means. And we also see here that when we have our temperature increased to 973 K, which is 700 degrees Celsius, we see here that we become much less spontaneous. It's only minus 12.12 kilojoules per mole. So just a couple of things to just kind of glean from this problem before we delve any deeper into it. We can see that as we increase temperature, the reaction spontaneity decreases. So that informs us, without even knowing anything about the values of enthalpy and entropy. If the spontaneity decreases as we increase temperature, that must mean that entropy is unfavorable. Entropy is not helping us in this case, because if we add temperature, we actually see our spontaneity go down. So in this problem, as we can with a lot of them, just knowing the temperature dependence of the free energy can allow us to make an inference as to which term is being favorable here. And in this case, we can see that it must be that this is an exothermic reaction. And so the enthalpy is helping us, entropy is not, and as we increase temperature, the reaction actually becomes less spontaneous. So with this problem, part 1 asks us to actually go ahead and calculate the equilibrium constants at these two different temperatures. And so this problem brings in the last of a set of equations that we're going to use in this chapter. And the first one here is that delta G is equal to minus RT ln of K. And so what this equation allows us to do is walk between free energy values and equilibrium constants for a given temperature, and then this is our R constant. So since we're given delta G values here and we want to calculate K, we need to do a little bit of manipulation. Okay, and hopefully everybody's good seeing that we can get our minus RT over here underneath the delta G, and then we can take E to the both sides to get an equation that shows that the equilibrium constant is equal to E to the minus delta G over RT. So what I'm going to do is for both of these temperatures, I'm actually going to calculate this minus delta G over RT term and then take E to that term to give me the equilibrium constant. So let's first do that at 298K. So at 298K, our delta G, again at 298, is equal to minus 141,600 joules per mole. I'm going to convert this into joules per mole because my R constant is going to be in units of joules per mole Kelvin. So if I calculate my minus delta G over RT term, that's going to be equal to minus 141. So we're going to have a double negative here, so that negative is actually going to go away. And we've got 8.314 joules per mole Kelvin times 298 Kelvin. So going ahead again and solving for my delta G minus delta G over RT term, I get positive 57.2. So if I take E to the positive 57.2, I get a very large number here. I'm going to get 7 times 10 to the 24th. So this is, again, a very large number. And we'd predict that, right? If we have a very large negative delta G, again, remember my slingshot analogy, I talked about that as being a huge thermodynamic driving force so that we are going to be able to reach products, and a very large equilibrium constant, again, means that we lie on the product side. So doing the same calculation now, not at 25 degrees C, but at 700 degrees C, so that's our 973 Kelvin, delta G at 973 equals, it's still negative, it's still a thermodynamically spontaneous process, but now it's negative 12,120 joules per mole minus delta G over RT is equal to, in this case, we're going to have the double negative again, 8.314 joules per mole Kelvin. But now again, I have to put my new temperature in. That's 973 K. So now my delta G over RT term, my minus delta G over RT term, is a much smaller number, 1.5. So E to the positive 1.5 actually only equals 4.5. So again, if we had an equilibrium constant of 4.5, this is barely on the product side. So by looking at something we maybe are a little bit more familiar with since we've had 3 chapters on equilibria, we can see that as we raise the temperature, our equilibrium shifts from very product favored to almost an equal distribution of reactants and products. And again, that's consistent with our entropy not being something that helps us, because as we increase temperature, our equilibrium shifts from very product favored to very kind of neutral between products and reactants. Okay, so that kind of solves the first part, which is just, again, getting our legs wet with our feet wet with this equation here and using this equation to interconvert free energy and equilibrium constants. But again, the logic makes sense based on what we understand for this reaction. The next part here tells us that we have 2 containers that we're going to fill with these quantities of the 3 gases. We're going to keep one at 25 degrees, and then we're going to have one at 700 degrees. In which direction, it says, if any, will the reaction proceed to reach equilibrium at each temperature? So when we see things that say, in which direction will our reaction proceed, what we really want to think about is a Q versus K comparison. We need to say, where are we at? And then ask where we want to go. And we just calculated our K values. And then we'll see, again, which way we're going to shift. So let's go ahead. I'm going to get a new piece of paper here to go ahead and calculate our Q versus K parameters. So I'm just going to rewrite our equation up here to remind ourselves. So 2SO2 plus O2 gives 2SO3. And again, if we write our Q expression, again, we're considering this to be an equilibrium. Q is equal to the partial pressure of SO3 squared over the partial pressure of O2 times the partial pressure of SO2 squared. Just, again, a standard way of taking this equilibrium equation and writing an equilibrium expression. Putting in the values that they provided for us, the concentrations that they provided here, again, 0.5 molar or 0.5 atmosphere SO2, 0.01 atmosphere O2, 0.1 atmosphere of SO3. So again, I'm going to put these values in here. I get a Q equal to 4.00. So what we need to do is we need to compare Q versus K, and we'll see if we're before the equilibrium or after the equilibrium. So again, our Q is 4 at 298 K. Our K was equal to 7 times 10 to the 24th. So in this case, Q is much less than K, and so our reaction will shift right. And again, we're going to know that this is going to be a very dramatic shift. And that's not surprising. We already knew based on the very large equilibrium constant that we'd have a significant shift to the right. And so when we have our concentrations that we put in here, we're at very far from where we want to be, and so we're going to have a significant shift. However, when we have our higher temperature, right, and at 973 K, we had our K equal to 4.5. And in this case, Q was still less than K, so our reaction will proceed forward, but we're going to barely move forward. So we will shift right because Q still is less than K, but we're going to shift very minimal. So very minimal shifting here because we're almost at where we want to be. But one of the things that we can point out here that is important to say is that our delta G still is negative for this process. And by our delta G being negative, that means we can still use the same reaction and move forward to get from where we're at to where we want to be, right? And so in this case, we do see that we will shift forward still. If Q was greater than K, we covered this in sample problem 20.9, if Q is greater than K, you've actually gone past your equilibrium point, and the delta G for that process will actually be positive. All right, so that's parts A and B. We used our new equation here to calculate the equilibrium constants based on the free energy values. We kind of said, well, let's set up a situation that's not our standard state, not 1 atmosphere for each of these. And we kind of said, where is our Q versus our K? And we kind of compared where to go. The last part of this problem is to then calculate a delta G, which is different from a delta G naught. The delta G is for this system in part B. So using our non-standard conditions, we're not at 1 atmosphere for all of these. And we're going to calculate what the actual delta G is for that condition. And that brings in the last of our equations that we have here. So for part C, we're going to use the last equation from the end of this chapter. And that's really saying that you can have a delta G when you're not at standard conditions. And for this one, we'll just put for 298. That's going to be equal to the delta G when you are at standard conditions. So again, this is going to be 1 atmosphere. And you add to that RT ln of Q. And so if we were at standard conditions, if we had our Q such that all of these were equal to 1 atmosphere, 1 squared over 1 times 1 squared is going to be equal to 1. The natural log of 1 is 0, so this term would disappear, and we would have no change between our delta G values. But because we are at non-standard pressures, we're going to have a different delta G. So we just need to go ahead and put in our values for Q that we calculated in part B and delta G naught, which we had from part A, and figure out what our non-standard delta G value is. So I'm just going to go ahead and do that, and I'm going to change again these, we have to change our units because we're going to have our R is joules per mole. I'm actually going to go ahead and change that one to kilojoules. Because you'll see at the end here, we're still going to end up with a fairly large value. So 141.6 kilojoules per mole is what our delta G was at 298. R is again 8.314 joules per mole Kelvin. Again, I'm going to change this value into kilojoules. So 1,000 joules is in 1 kilojoule. Our temperature is 298 Kelvin. And the natural log of 4, because that was what our Q value was that we figured here. So go ahead and run through this, and we'll see that we're actually only going to decrease. This is going to be a fairly small number, even though the natural log of 4 is going to be a positive number. You know, going through here, this is not going to be a significantly large number that we're going to detract from this. We actually get minus 138.2 kilojoules per mole. So at 298, and we can see this, we saw this up here, where we're at was very different from where we wanted to be. And so even though it wasn't standard state, it was still a situation where we're going to have a large thermodynamic driving force to get us to our equilibrium where we want to be. And not surprisingly, when we run through this same calculation here for delta G at 973, again, that's delta G naught for 973 plus RT ln of Q. And so we're going to have minus 12.12 kilojoules per mole plus 8.314 joules per mole Kelvin. Again, converting this into joules. And we have to make sure to put in our different temperature here. So 973 K, and it still times the ln of 4. So in this case, our delta G is minus 0.90 kilojoules per mole. So as we already kind of predicted up here by a Q versus K comparison, we're going to have a very minimal shift to the right. And again, a very minimal shift to the right means that there's not very much thermodynamic driving force to take where we're at, our Q, right, these conditions, and get where we want to be. So we used our analogy of our slingshot. So in the A situation, 298, we've got a large thermodynamic driving force. We're at a position that's very far from where we want to be. A lot of thermodynamic driving force to get us there. When we increase the temperature, now we have a situation where we don't have a lot of thermodynamic driving force, and that's okay because we're shifting very minimally to the right.